Hello, fellow problem solvers. So they're going to be doing a number theory problem from the 1994 IMO, problem number pre-4. I suggest you try this problem out for a minimum of 10 minutes, ideally 30-ish to 45, not more than an hour and a half. If you're just getting comfortable with number theory, you want to try an IMO problem that's easy-ish, this is a good problem to try. And now, without further ado, if you want to go along with us, pause for 5 minutes, put your first ideas out on paper, and now let's begin. You just find all ordered pairs of m and n, where m and n are positive integers. I usually like when they use x and y instead of m and n because they're so similar to each other, m and n. And it's hard to say m and n, m and n, m and n instead of x and y, such that this is an integer. So n cubed plus 1 over mn minus 1. What does this condition mean? It means one thing. It means that m times n divides n cubed plus 1. That's what a condition means. Just like that. And how are we going to use this condition, right? That is the question here. So for me, when I see this, I go, is there a way for me, actually, n minus 1? And when I see this condition, I go, okay, this is a high power, a power of 3, a power of 1, maybe 2, if you're considering m times n to be something. Let me get this to a lower power, right? That's the idea I have in mind. But I can't do it if I have n. I don't have anything with m here. So what I'll do here is I'll say this divides m times n to the cube plus 1, which is m n cubed plus m. Okay? So now can I make something that mn minus 1 divides that has this thing? Because now this is of power technically 4 if I'm considering m and n to be different. So I'd be of the same size-ish. And how can I do this now? So I need to get something that this divides that I can then subtract from this. And the quickest thing is it divides mn minus 1 times n squared, which is equal to mn cubed minus n squared. And now this minus a divides b, a divides c, then a divides b minus c gives me mn minus 1 divides this minus this, m plus n squared. Now there's something that's also a bit interesting to me about this, is this is not symmetric in m and n, though can I make this symmetric in m and n? And this is just an idea I had that I want to show with you, is that this also divides mn minus 1 divides n cubed plus 1, but also divides m cubed times n cubed plus 1. Why do I write it like this? I write it like this because now I have this is n cubed plus m cubed. But this is, think if m times n is equal to x. This is x minus 1 divides x cubed plus something. But I know x minus 1 divides x cubed minus 1 because I can factor it. So if I add a 1 here, I subtract a 1 there, I get mn minus 1, because it does divide this, it needs to also divide m cubed plus 3, m cubed plus 1. So now I have that this condition, in fact, is symmetric with respect to m and n. And so if I have this thing, I can get this thing, which means if I have this, I know I can analogously get mn minus 1 divides n plus m squared. And this I'm telling you just to show you different ways of thinking. Now, I think if I just said this divides m times m plus n squared, which is equal to m squared plus mn squared, I could have done this same thing I've done before. Just get mn out of this, and this is equal to m squared plus mn minus 1 times n. So I've subtracted an n, I need to add an n, and I'll get the same thing. Now I have mn minus, so I can't put it to a lower power than I have it already here. So if mn minus 1 divides this, and it divides this. This is now symmetric in m and n. What do I do here? I invite you to pause for another 10 minutes and try to push the problem further. And the answer is, well, I have, n squared is really the big thing on this side. When I have the divisibilities, I have, mind you, both of these are non-negative, these are positive integers. So I have that, actually there are two ways to go about this. One is to say, I have this sort of inequality on both sides, n plus m squared. And now I can add these two inequalities and get m squared plus n squared. Now, minus m 2mn plus n plus m plus 2, when I get the minus 2's on this side, is greater than or equal to 0, which is true. Actually, I don't get anything from this. I thought I would get something from this, but I don't. But the thing is, can both of these things be true simultaneously? And what I'm trying to get at here is that if m is greater than n, if m is equal to, say, 2n, then the inequality then this inequality seems less likely, because this is equivalent to 2n squared minus 1 less than or equal to 2n plus n squared. Kaboom, kaboom, and I get n squared minus 2n plus 1 less than or equal to 2. And this really this constrains, this is n minus 1 squared less than or equal to 2. That means n is either 1 or 2 here. So I can, without loss of generality, assume m is greater than n. If they're equal, I can solve this, right? I can solve this immediately. If they're equal, I'll get n squared minus 1 divides n squared plus n. So I do minus 1 plus 1. Then I have n squared minus 1 divides n plus 1. And now this is equal to n plus 1 times n minus 1. I get that n minus 1 needs to divide 1. And so n is equals 2. So I get one solution is 2 if they're equal. If they're not equal, let's assume m is greater than n. And I invite you here to pause for 5 minutes and try to solve this. And what I get is, like, if n is greater than m, I get this. And now you might be thinking, oh, but wait, it's actually kind of difficult for me to now try to just use the inequality to get what I want. What do I do? And I don't know, honestly. Let's try out a couple of different things. One is, n is greater than m. Let n be equal to m plus t. And then I have this is less than or equal to. So this is going to be m squared plus m plus t. And this is going to be m times m plus t minus 1. Now this is equivalent to m squared plus mt less than or equal to m squared plus m plus t minus 1, which is now equivalent to mt. Actually, this is mt minus m minus t. Actually, this is a plus 1. Plus 1 less than or equal to 2. Why'd I write it like this? If you have a times b and a plus b, or k times a, k plus k plus b, plus k times b, you can factor this. And it's a thing you get from practice. You just see this time and time again. And you have this is m minus 1 times t minus 1 less than or equal to 2, which means what? Well, it means that either t is equal to 1, or that, what's it called, m is equal to 1. Or they can both be equal to 2, right? Those are the possibilities this gives you. This, mind you, this is an inequality, not the divisibility. But from the inequality, so we can just, let me write out those cases, like case 1, t is equal to 1. Then I have this thing right here, 0. But then I know n is equal to m plus 1. And then I have m plus 1 times m minus 1 divides m squared plus n. Actually, now that I think of it, I could have done something more. But you know, this is a more natural process, a more actually plus n is plus n plus 1. I feel this is a bit more natural, like how the thinking actually goes by when you're trying to solve the problem. Is you try, you know, if n is greater than m, and we try to put this. Like this is me using that this is an inequality, and t here is greater or equal to 1, and t is a natural number. So from here, I get this divides also m squared plus m minus 1. I subtract this from this, and I get m squared plus m minus 1 needs to divide 2. And this is incredibly limited. This means that m is equal to 1. Why? Otherwise, this is equal to m times m plus 1. We have 2 is greater or equal to this, so I have m times m plus 1 is less than or equal to 3. It can't be 2, it can only be 1. So this really does imply m is equal to 1, which gives us a solution 1, 2, and 2, 1. Right here I just do that. M is greater than n, I'll have the symmetric solution on the other side. So this is what gives me these two solutions. Now, the second case, t is equal to 2. And actually, let me do the case where m is equal to 1. And then what do I have? I have n minus 1 divides 1 plus n. Subtract this from this, you get n minus 1 divides 2. And so now n minus 1 is either 1 or 2, which gives us n is either 2 or 3. So we get 2, 1, the thing we had before, which we already have. So we get 3, 1, and 1, 3 as solutions. Now this is the second case where m is 1. And now we have the third case where neither m isn't equal to 1, t isn't equal to 1. And now both of these are, what's it called? So now we have that if t, like both of them need to be less than or equal to 3. You can check out all the cases, but let's just put t is equal to 2 as the first case. That implies m minus 1 is going to be is an element of 1 or 2, because this is less than or equal to 2. And now what do we have? Like we can literally just go case by case and check this out. What do I have? I have m squared. I really kind of don't want to check this case by case now. Okay, this is a way for us to do this. Let's just be realistic. This is a way for us to, this is not a lot of cases. This is a way for us to do this. T is equal to 2 gives us this. So m is an element of 2 and 3, which makes n is equal to m plus t, which is then an element of either 1 plus 2 or 1 plus 3 is an element of 3 and 4. So let's try m is equal to 2, n is equal to 4. Does that give us a solution? It gives us 8 minus 1 divides 4 plus 2. Doesn't give us a solution, so this one fails. Like this is what m and n are constrained to be, but not what they won't satisfy necessarily if this is the case. And I think, though actually I'm a bit sus about this being the case. Oh no, this is okay, I'm not sus about this case. I'd be sus about m equals 3, n equals 5. Why am I sus? Because I have equality here if m is equal to 3, t is equal to 2, then I have this is equal. And this is just the divisibility condition we had. That's why I was a bit sus. I thought this was the divisibility condition, but it's not. If we have 3 and 5, we have 15 minus 1 is 14, divides 9 plus 5, which is equal to 14. This is also a solution, so we get the solution 3 and 5, 5 and 3. And finally, we have the case where t is equal to 3. And now this forces m minus 1 to be equal to 2. m minus 1 to be equal to 1, which means m is equal to 2. And now we need to check the solution 2, 5, which should also work because then this is equal to 2. And for 2 and 5, we have 10 minus 1 divides 2 squared plus 5, which is correct. So we have the solution 2, 5, 5, 2. Incidentally, these are all Fibonacci numbers, all these pairs. Maybe there's something to that. That's just a little bit of an interesting, maybe there's nothing, maybe it's an accident, who knows. Like, you don't have a lot of numbers for us to have like, oh wait, this is actually f of n. This is how we've done, it's very technical, this problem. You know, you're trying to, you get this divisibility condition to something smaller, and then you also notice you have the symmetry. You can get it to m squared plus n and n squared plus m. And so you notice, okay, but I can't really have both be true. And then you finish the problem. This finishes up our nice little number theory problem from the 1994 IMO, problem number 4. And as always, thanks for problem solving.